So, as we are discussing the crystal structure of silicon or gallium arsenide, we have seen that, and in different directions, like whether you are taking 100, 110 or 111, you have different kind of crystal arrangement. What does it mean? Different kind of crystal arrangement means that how many atoms are or one atom is connected to how many atoms inside the bulk, that number is different. So now we will see that how it looks exactly in real life. Like let us say this is the crystal structure, so you have at different corners atoms are sitting, and then you are cutting it with 111 plane. That means you are cutting it like this somewhere. So if this is x axis, this is y axis, and this is z axis, then x axis, y axis and z axis, all the axes are cut by this plane at 111 or AAA, right. Now as you can see, so this plane is 111 plane, and it is cut x y z axis in like x equal to a, y equal to a, and so there is a mistake, this will be y equal to a, okay. This direction or the plane has cut the xy plane in along this line, right, and this is 100 direction, this is 100 direction, right. Now to calculate the angle between two crystallographic direction like u1 v1 w1 and u2 v2 w2, from coordinate geometry we can see that this is the formula, like cos theta is equal to u1 u2 plus v1 v2 plus w1 w2 divided by their own distance. Is this actually, you know that if there are two vectors a and b, then a dot b gives you ab cos theta, right. So cos theta is equal to a dot b divided by a into b, like the mod of a into mod of b. So this is just like this, the same formula, right. So this is the dot product and this is the divided by their own length, correct. Now the angle between this 111 plane and 100 plane is what, like it will be 1, it will be on the top side, it will be 1, and there you will have like 3 into 1, so it is 1 by root 3, and that will give you 54.735 degree. So now the point is that while you are having this, let's say this is the block, and this is let's assume that this is the 100 plane, right, this is the 100 plane, then this 111 plane will cut like this, and this angle, like what the 100 plane and 111 plane has made, this angle is 54 degree or 54.73 degree. So as we were discussing, this is the 111 plane, and then this 111 plane intersects, this 111 plane intersects the like xy plane at 110 line, right, at 110 line, correct, because here if you see, then if you draw a plane at this 110 line, then it will be parallel to the z axis, right. So this is 110 line where it is intersecting. And another thing is, so as we already know that xy plane is parallel to 001 plane, right, because at 001 plane it has cut the z axis at 1 or z equal to a, let us assume, then xy plane is parallel to that plane. And another point, very important point in this regard is like 100 plane, let us say this plane, then 010 plane and 001 plane will be the two different plane which will be perpendicular to this 100 plane, right. So this plane, if it is 100 plane, then there are multiple planes we can draw, like infinite number of planes which are perpendicular to the 100 plane, right. Like this plane is also perpendicular, this plane is also perpendicular, this plane is also perpendicular, but in that there are only two planes which will be like the basis plane, right. So let us say if this is the 001 plane which has cut the z axis, and then if then this is 100, then this will be 010, right. Now the important point is that all of these plane are called like 100 plane family, and crystallographic direction wise they all have the similar kind and crystallographic direction wise they all have similar kind of property, similar kind of material property, like the way we are discussing earlier, that in different direction the atoms are connected to the bulk by different number of bonds, and in this family of planes, like an atom which is in 100 plane, let us say the crystal is cut in 100 plane, then an atom at the surface will have same property if the crystal was cut in 010 plane or in 001 plane. Basically, while the silicon wafers are prepared or manufactured, they are manufactured in a cylindrical shape, like in ingots. So the single crystal silicon ingots are first formed, like it will look like a cylinder, and then different slices like circular discs are chopped off from the cylinder. So these are called wafer. These are usually like 400 500 micrometer of thickness, and it can be, its diameter can be 2 inch, 3 inch, 4 inch, 6 inch, or even 12 inch diameter. So these are like thin, very thin plates. Now as we discussed, that different planes have different kind of material property, right. The atoms present in different plane have different kind of material property. Now one ingot, once prepared, ingot is like a cylinder, as I am saying, then it can be cut in different direction, whether we are cutting at 100 direction or 110 direction or 111 direction. Depending on that, the silicon material will have different kind of properties, right. And to understand that, we introduce this primary flat and introductory and secondary flat. What is primary flat? So there is a long cut, so this is not properly circular, rather there is a long cut at the edge which is called primary flat, and then there is another small cut which is called secondary flat. Now for 100 wafer and n type wafer, you also are aware of the term doping, where we can dope the silicon semiconductor to be p type or n type. P type semiconductor will have more number of positive charge carriers or holes, and n type semiconductors have more number of negative charge carriers or electrons. Now for a 100 cut and n type silicon, the primary flat and the secondary flat are exactly opposite way. So by seeing this arrangement, without even asking, we will know that this is 100 n type silicon. Similarly, if the secondary flat is present at the perpendicular direction to the primary flat, then it is 100 p type. It is 100 p type. Again, if the primary flat is very close to the secondary flat, then it is 111 cut, and this is n type, right. And if there is no secondary cut, no secondary flat, then this is 111 p type. So like this we can identify which kind of silicon wafer our sample is. So now we will discuss about this flat, and one important thing, I will go back few slides back where I have shown that 111 plane intersects the xy plane, or the let us say 001 plane, we can call it 001 or 100 plane in the along the 110 line, and the cut what we make on a silicon wafer is along that 110 line. And why is that? That will come later, but currently already from the crystallographic orientation, as we have discussed, you know that 110 plane has like one atom on 110 plane have only one atoms connected to the bond or the bulk. So this is most unstable plane, whereas 111 plane or the 111 plane is the most stable plane, right, because one atom is connected to the 3 atoms at the bulk. So while we make the cut is automatically formed, like the open surface at the cut is 111 plane, and along the line 110 line actually the cut is made. So about that we will discuss more while we go to actually etching and cutting. So this is one thing. So 111 plane intersects the 100 plane at 111 at 110 line. Okay. Now the 111 plane is called cleavage plane, because if we scribe through the line parallel to the primary flat or even perpendicular to the primary flat and press the wafer gently, then the wafer will break along that line. Okay, because along that line we have already the 110 line which is most fragile, right, and then it meets the 100 line, like the 111 plane which meets 100 plane at this line. So it will just break at that point. So as we see, while we will see the lithography, that time also we will discuss this, that usually the primary flat is also used to align the pattern for anisotropic wet etching or anisotropic chemical etching. In summary, like the atoms on the 110 plane of silicon are bonded to the next 110 plane with one bond, or only one atom is bonded. Atoms of 100 plane of silicon are bonded with two bonds to the next 100 plane of the crystal, and atoms of 111 plane of silicon are bonded with 3 bonds to the next 111 plane. As a result, the binding state in 111 direction is the highest, whereas it is considerably lower for 100 and the lowest in case of 110 direction. And because of that, the etching rate or the damage of the wafer along the 110 direction is the highest, whereas 111 direction it is the lowest. Now micro machining processes, in that there are two specific different processes. One is called bulk micro machining and another is called surface micro machining. So before we go to micro machining, we need to understand one thing, that is currently in macro scale we make different devices or different structures, and for that we have already some specific processes are set up in the industry, right, like we can, if we want to make this, so if we want to make this, then this has some kind of mold where the material will be put in that mold, and then it can be made from that. Or also like if we want to make some particular kind of design on that, then accordingly we can cut it, or we can polish it, or we can scribe it to make exactly that pattern. But this is possible only because this is in macro scale, right. But if we need to do the same thing, like while we are making a micro scale device or nanoscale device, then we need to make this kind of structures in very small length scale, like in micrometer scale or in nanometer scale, right? Like in the first module we have talked about cantilevers and membranes, right. If we have to make a cantilever which has a length of 100 micron, width of 5 micron, and let us say thickness is something about 500 nanometer to 1 micron, then using our popular macro scale processing techniques, it is not possible to make this kind of devices, and for that we need to use a separate kind of process flow, and that is called microfabrication or micro machining. Now in that case the material is also very important, as we were discussing earlier also, that the material is very much important, and this silicon is chosen as the material because it has extraordinary properties, like it has good mechanical properties also and good electronic properties also. And another important point is, as we just discussed in last few slides, that it has a single crystal structure, right, and in that single crystal structure it has a very defined property in each of the direction, and accordingly we can make our device according to our requirements. So let us first go to micro machining, bulk micro machining. So in bulk micro machining we start with bulk silicon wafer. So as I was saying that for silicon, like manufacturing of silicon is done by processing these ingots, right, which is cylindrical in shape, and then we cut the ingots parallelly, slice by slice, and then each of these slices are used as a for microfabrication or as silicon wafer. Now we can remove material until the final surface is created. So there are different techniques which a few of them we will discuss in the part of this course, that how we can remove a material. And while we are removing some material, let us say if this is some material and then I am removing some material here from the circular some circular this kind of region I remove, then it will create a circular hole or a hole in this block, right. So removing material is very much important, and we will see few of the processes, and then we can select a particular region which we want to remove and the another region we do not want to, right. So there are some masking layers or etch stop layer which we can put where we do not want to etch. Let us say if I want to write a pattern like A here, then only according to the A pattern I will etch, rest of the region I will just mask it so that it will not be etched. Then there are some bulk dry etching technique also. So other than using only liquids or liquid chemicals, we can use gases also for etching away the material. So that is, these are called dry etching techniques, and RI or reactive ion etching is one of the very popular technique for dry etching. And depending on our requirement we can also bond two wafers. So let us say we have a device such that on one device we have made some patterns and on another device we have made some other patterns, and for our application we need to bond it together. So that also is possible using bulk micromachining techniques. While I am discussing about bulk micromachining, the first point is that etching or wet chemical etching. In that wet chemical etching can be of two types, one is isotropic and another is anisotropic. So in isotropic etching what happens, that in all the direction etchant will etch the material in all the direction equally. So let us say here these regions are properly protected with some etch stop layer. So this region, so this is the material or your substrate or your sample which you need to etch, and this brown color regions are like etch stop layer. So this will not allow these regions to be etched. These regions will not be etched, but these regions will be etched, and in all the direction, if we take in this direction or in the other direction, all the direction the etching rate is same. So you can see that as it has gone down vertically to some etching distance, it has gone sideways also, and after certain time it will start etching from the bottom of the etch stop layer also. So there is under etching or side etching also, right, and in that case all of the sides are etched equally with same rate. And if you change the chemical, if we change the chemical and take different chemical, then we can use it with some different rates, but in all the direction the etching rate will be similar, will be same. Now we can also etch it with some kind of agitation. What does it mean? Agitation means we can sonicate it with some particular frequency. Now while we are sonicate it, we are allowing the liquid to move sideways even more freely. So those liquids will get in contact with the surface more frequently, and also whatever is the product of the reaction, that also will be removed very easily. So in that case the etching rate sideways will increase even more and we will get more etching rate. So one of this example is silicon etching with this HNA agent. What is HNA? HNA is hydrofluoric acid, nitric acid and acetic acid, and hydrofluoric acid and nitric acid reacts with silicon to make this SiF6 product, which is soluble in water. So it easily get dissolved and then the NO goes out. So the silicon is etched by this HF. Here what happens is actually HNO3 oxidizes the silicon to SiO2 or silicon dioxide, and then the silicon dioxide reacts with HF and makes this SiF6 product, which is H2SiF6, and this is very much soluble in water, right. This fluoride is very much soluble in water, so it easily get dissolves, and accordingly silicon will get etched in all the direction equally, and equally, right. Here the acetic acid is a moderator, that means that it actually does not do any reaction, but it has a dielectric constant which is very much lesser than the H2. So it prevents the HNO3 to break into NO3 or NO2 and allows formation of species that are directly responsible for oxidation of silicon. So it does not allow or actually reduces the rate of HNO3 dissociation. Okay. So acetic acid actually reduces HNO3 dissociation, and because of that HNO3 will be more capable of making silicon to SiO2, and that SiO2 will react with the HF and ultimately will make this dissolvable product. So accordingly we can get silicon etching. And here one important point is, as I was saying earlier, that the silicon has different etching rate in different direction. So then the HF reacts with SiO2, and forms this H2SiF6 product, which is actually dissolvable in water, and because of that silicon gets etched very easily with this HNA agent. And here the acetic acid is a moderator, that means that it does not etch or does not react actually with silicon or even any byproduct of this reaction, but it reduces the dissociation of HNO3 because it has a very less dielectric constant than water. So the HNO3 will not dissociate into NO3 and NO2 into the atmosphere. So it will be available for oxidizing the silicon to SiO2. Now another important point is here, as we are saying that this HNA agent is etching in all the direction equally, but as we have seen from our crystallographic orientation class, that in different directions silicon has different etching rates. What does it mean? Different etching rates means in a particular direction, let us say if this is 100 direction, then in that case one atom is connected to two atoms at the bulk, right. So and whereas if this is an 111 plane, let us say if this is 100, then this says this direction or this direction will be 111, and in that direction one atom is having more number of bonds or 3 bonds to the bulk, so that is more stable. Now if we put this material here, then this is 100 direction, and in this direction, whereas this is actually this is another 100 family, whereas 110 there will be this plane as 111, which will be the lesser etching rate, and in that case it should have been It should have been that the one direction it is more etching and another direction it is different kind of etching, but it is not, it has not happened in this case, because HNO3 is such an aggressive agent that it easily reacts with silicon and completely etch it away in all the direction. But in the next class we will see examples where we will use KOH or TMH as the KOH or TMH for silicon etching, and there we will see that in the 100 direction and 111 direction have very different etching rates, and accordingly different kind of geometries are created using this anisotropic etching. Whereas in HNA, in case of hydrofluoric acid, nitric acid and acetic acid combination, this is isotropic etching. Now, as I am saying that this HF, HNO3 and acetic acid are like a mixture which etches silicon very aggressively and very easily, but depending on the different concentration it has different etching rate. Like if we use 10:30:80 HF, HNO3 and acetic acid, then we will have an etching rate of 0.7 to 3 micron per minute. That means 700 nanometer to 3 micrometer per minute. Whereas if we use more HF and more HNO3 and very lesser amount of CH3COOH or acetic acid, then in that case it will be 4 micron per minute. And here you should understand one thing, that acetic acid is like just a moderator, or it actually just controls the reaction so that the HNO3 is not dissociating into the solution, but it does not actually react. So increasing HF and HNO3 in with respect to acetic acid actually increases the etching rate. 9% of HF and 75% of HNO3 and 30% of acetic acid, then we get an etch rate of 7 micrometer per minute. So more acetic acid is will make the HNO3 will make the silicon to more in SiO2, and that SiO2 will get etched by HF and we will have more amount of silicon etching. Here we see that in the first case where we have like 10:30:80 or 1:3:8, that time SiO2 is, if we use SiO2 as masking film, then that will be also etched as 30 nanometer per minute. In the second case we can use Si3N4 or silicon nitride as the masking film. The etch rate there is very small. Whereas in the last case where we have a lesser amount of HF, in that case we can use SiO2 also as the masking film, but here the etching rate is of SiO2 is 70 nanometer per minute. So by the time it will etch the silicon to 7 micron, it will etch the SiO2 to 70 nanometer. So if we, what we need to understand in this term, that let's say I need silicon to be etched about, let's say 700 micron, and for etching 700 micron, if I am using the last recipe or this third one, then for 700 micron etching I need 100 minute of etching in this concentration, right? But in this 100 minute, this SiO2 also will get etched till 70 into 100, that is 7000 nanometer or 7 micron. And so 7 micron etching, 7 micron SiO2 film at least is required to protect the Si from etching, and so depositing 7 micron SiO2 or silicon dioxide film is very difficult. So this is not a proper solution, and we need to so keep in mind all the time that even though we call one layer as masking layer or the etch stop layer, that layer also has a very has a etching rate which might be very small, but depending on the time that may also get completely etched. So next time we will start with anisotropic etching. Thank you.